Alongside the really famous fossil deposits, there are quite a few exceptionally preserved biotas that are not as spectacular and definitely not as well known, but they're still important for helping us to reconstruct the history of life. So this one is from the Early Ordovician of North Wales, called the Afon Gam Biota, and is one of the lesser Burgess Shale-type faunas. But it's still really, really interesting. Hello everyone. Firstly, I just want to say that I wasn't anticipating doing this video next. I was intending to do, with Lucy actually, a follow-up on the Dickinsonia movement video, looking at answering some of the recurring themes that have turned up in that enormous list of questions and comments, and it's wonderful to see them, and I'm sorry I haven't been able to respond to as many as I'd like so far. The reason is that I took a bit of a high-velocity tumble on a tennis court and have wrecked my shoulder, which has been a little bit of a sort of distraction going to get x-rays and not being able to sleep and stuff like that. So I thought in the meantime I'd do something easy that I know well and it's still going to be entertaining. But we haven't forgotten the rest of it, and we'll get back to it once I can sort of stop taking painkillers and things like that. Nothing's broken, I hasten to add, just I never knew you could sprain your shoulder like that, but apparently you can. It's always a learning experience, isn't it? Right, the Afon Gam Biota. As many of you know, most of my work has been based on Ordovician rocks, partly because that's where I started out on, and you just carry on with inertia basically in this sort of field, and partly because it's such an amazing and extraordinarily interesting part of the history of life. So the Ordovician follows on from the Cambrian, and it also shows an enormous biodiversification event. It's very different to the Cambrian explosion, in my view, although others have argued that it's just a continuation of it. But what we see during the Ordovician is a remarkable diversification at lower taxonomic levels, at the same time as a radical overhaul of the ecosystem structure, the way that faunas function. And this is something I'll have to do a whole video on at some point, probably fairly soon, because it's kind of background to a lot of the other stuff. But the Great Ordovician Biodiversification Event is a really, in some ways, still mysterious interval, because there doesn't seem to have been a particular trigger. It's just ecosystems, at least this is the way I read it, reached a certain point of complexity and then just accelerated. So we soon have a tripling, quadrupling of the number of species that we see in the fossil record. We have whole new types of ecosystems being developed, like coral reefs, for example, bryozoan mounds, all sorts of things going on. And we also have much more segregation of communities on a small scale. There are many more different types of ecosystems within a small region, whereas in the Cambrian it would have been more or less homogeneous. So there are major differences in how ecosystems were being structured around this time. So it's obviously studied quite extensively. There's quite a lot of people around the world who are interested in this field. And we don't have any definite answers yet, but it just doesn't have the glamour of the Cambrian explosion. But it is in many ways just as revolutionary in terms of how it dictates the future of animal life, especially in the seas. So one of the things we do know so far is that it is different for different groups. You have diversification in brachiopods at a different time from trilobites, at a different time from sponges, and so on. And even within one group, it's different in different continents. It's not something which was a correlated global event. It seems to depend on which data set you use, where you've been studying, what the rock types were through this sequence. And the overall pattern is probably just that we are seeing small bits of the overall pattern. So we are not actually seeing the whole story anywhere because we don't have a good enough fossil record. It's always intermittent, incomplete, it's biased in different types of environments and so on. So we are always limited by that. And if you combine everything together and take a sort of average, then it looks like most of the diversification happened during the middle and the early part of the late Ordovician, and the late early part as well. But the earliest part of the Ordovician, the Tremadocian especially, seems to have been effectively a continuation of Cambrian faunas. And then you get a spectacular increase starting in the later Phloian, Dapingian, Darwinian, that sort of time. But we are limited in one critical way, in that this is the Ordovician and it doesn't have the Cambrian Burgess Shale-type faunas. We actually have a relatively limited record of Ordovician conservat Lagerstätten. Until 20 odd years ago, it was much more limited. There were only sort of 3 or 4 good ones that were known around the world. And they were all restricted in particular ways. So you get extraordinary faunas like Beecher's trilobite bed, which is telling you about one particular very deep water semi-anoxic environment, which was dominated by Alini trilobites. Or you have the Suma Shale, a periglacial lagoon from near the South Pole with wind-blown dust and really weird chemistry. It's a whole mixture of isolated things which you can't compare with each other. Things have been improving. So the last 20 odd years we have had quite a number of new Lagerstätten, but we still don't have much continuity in terms of being able to look at the same environment in relatively similar places and see how consistent they are. We also know that there are major differences between the diversification patterns that we see in Shelly groups like brachiopods and trilobites and in other groups. We know this on a small scale thing. So there is hidden diversity. So if you compare, for example, in our built inlier area, the brachiopods and trilobites, they give quite homogeneous patterns across the area. If you look at the sponges and the paleoscolecodon worms, it's nothing of the sort. Every fauna is different. So there's much more diversity that is still being hidden. And it might be exponentially more than we would expect because of differences in the ecology of different groups. There's a lot we don't understand. It really is. So any new exceptionally preserved fauna is actually really important. So back in 2010, we were put onto the possible existence of an interesting site by Richard Fortey, who recalled how decades earlier he had been working in North Wales on what he called the wettest day of his life, and which is quite normal in North Wales, and found some sponges by hammering some outcrops. They were just a few specimens in some nice mudstone. He somehow sort of managed to wrap them up, ran away with them, and retreated absolutely drenched. It's up in the mountains. It's quite hard to get to. Apparently, he never went back there. But he told us exactly where they came from, more or less, the right stream section. And so we thought, might be worth looking at. Complete sponges and not that common. We looked at their fossils, and they were very definitely complete sponges. These were not isolated spicules. In fact, it was quite difficult to see the spicules at all. What we could see was soft tissue. And this is when you start getting really excited, because although sponges are relatively easily preserved amongst exceptional preservation, or so it seems, they seem to turn up in most conservat Lagerstätten from marine sediments, they are really an unusual thing. You don't get them anywhere without exceptional preservation. And when you see sort of complete, almost slightly three-dimensional still, sponge bodies with porous walls and the osculum preserved, it gets really quite exciting. Because if it could preserve that, the chances are it could preserve a lot of other things as well. The only problem was that we were about to move to China for 2 years. And we wanted to know whether it was worth applying for funding in order to come back while we were over there to work on this site if it proved to be promising. And that's fine. And we were going off there in January and it was still the autumn. So we booked a few days at the end of November in 2010. And normally that's not too bad a time for fieldwork. So we thought, we'll get something out of it. We'll see whether it looks promising and know whether to go back. It turns out that that week was legendary. Temperatures down to about -20, heavy snow, beautiful clear days, but absolutely brutal for collecting fossils. It didn't get above freezing for the week. It was an hour's walk in across semi-frozen bogs where your feet kept going through the ice and collapsing into really cold water, muddy water. You had to wipe the snow off the outcrops before you could hammer. You could then hammer for a few seconds before your hand starts sort of jarring and your nerves start jingling. And then you have to jump up and down a bit to try to get the circulation going before you could get back again. It was an amazingly beautiful place to work. I mean, really incredible area up in the mountains in North Wales, not particularly high. It's a fairly barren valley, but the stream valleys where we were getting the fossils from were, really beautiful. Quite hazardous at times as well, but ice-covered rocks, steep ravines, it's all good. You kind of get used to that in this job. And we only had a few days. It was very hard going. We took a couple of volunteers with us as well. And it was enough. We found enough weird black bits that we knew there was going to be something there. Because all the things we were finding were not what you expect for a normal fossil site. They're what you tend to see when there's exceptional preservation, carbonaceous remains being preserved in some form, probably quite a lot of iron sulfide involved. So despite the fact that we'd not found a huge number of really interesting things, there were some sponges, there was some stuff that we didn't quite know what it was. And so we decided it was worth going back. And amazingly, National Geographic agreed. So we actually got significant amounts of funding, which we had to do some recording of as well. But we went back there in the summer, definitely in the summer, for a total of 6 weeks over 2 years. That was good. That was glorious sunshine for most of the time, with extra volunteers to help out, coming on for a week or two at a time. Richard Forty even came out to join us at one point, and then it wasn't sunny. And he later claimed that that was the second wettest day that he'd ever had in the field. But still, it was nice to see him. And, okay, so what did we find? Quite a lot in total, but not as much as we'd necessarily hoped for. The rock is hard, it breaks with very sharp edges, and it tends to be quite large slabs. That limits how much you can carry back, but what limits it more is how much exceptional preservation there is. There's a lot of low-level stuff. Black streaks, weird things all over the place, but not stuff with detail, not things you can work with particularly. It's a grey mudstone. It's slightly metamorphosed, but has been protected from high-grade metamorphism of the rest of the area by a large dolerite intrusion nearby, which sort of created a pressure shadow. And there are several outcrops within this long valley, and they seem to show a more or less consistent fauna. There were differences between sections, but it was differences of degree rather than differences of its very nature. So it was obviously fairly consistent through a reasonable thickness of rock. And it's just that the exceptional stuff wasn't abundant.
Joe, what are you doing here?
Well, we've got the stream running through the section which is full of loose blocks. And ideally, what we want in finding fossils is to know where they come from in outcrop. But to start off with, it's often very useful to get an idea of what's in the overall fauna. And then you can start tying in localities in the section in outcrop with the loose bits. So we're seeing what there is as sort of overall flavour of the fauna first, before we do the details. So all I'm doing really is just finding promising looking blocks and splitting them to see what's in them. So sometimes they split nice and easily. And very good. Try this one. A lot of them are very badly weathered inside, and there's not much you can do with this, to be honest.
So there's nothing on this one then?
Nothing visible at all, but there's so much weathering on top of it that you can't really see much. So just keep going, and there'll be other bits in the same block which are much better. Yeah, things like that, for example. See, often the specimens in this are very difficult to see, so we've come up with a very high-tech solution, which is to use one of these. Good old-fashioned plant sprayer, and it transforms the contrast. So you now see there is a lump of pyrite material down here. Let's just see if there's anything in it. No, that's just a random nodule. No sign of anything fossil about it. So we just carry on. This is actually a very badly sheared block. It's had little fault planes going through it, which makes it much more difficult to work with. So let's take a nice smooth one. That one's igneous.
So how many blocks do you think here have fossils in? Is it 1 in 2, 1 in 10?
Most of them have got fossils in. This one, for example, on the surface, you can see it's got burrows. But almost all of the fossils we see are things like burrows, which are extremely common and not very informative. So maybe 1 in 10 have something a little more interesting in. Maybe 1 in 1,000 or 10,000 have something which is really exciting. So you end up building up large piles of scree around you. And hopefully you're going to find you something, but the chances of that are, as I just said, fairly slim.
Oh, perhaps we'll come back later when you found something. Thank you, Joe.
I think this counts as coming back later. About 10 years later, but it does the job. The first thing to say is that we have got the age tied down by trilobites. But in particular, a thing that's historically known as Shumadia pusilla. I think it's gone by other names as well, but it's in the Conophthalus salopiensis biozone, which is named after Shumadia pusilla. Told you it had other names. And this actually ties it to the well-known sections in Shropshire of the Shinton Shales, same age as that. And this is actually quite well known already, and there have been previous papers on this area because this one, the main stream valley, is actually the type section for the base of the historical Arenig division of the Ordovician. So it has been studied quite intensively, and there are a reasonable number of papers out there, quite detailed ones, going back 100 years. And there's lots of comment in those previous papers about the rock being full of black streaks, which are not graptolites. And that is very true. They're not graptolites. For some reason, there are no graptolites within the Welsh Basin at this time. It's a bit of a mystery that we have no answer to. But those black streaks, what are they? Well, most of them are probably burrows or burrow linings. Organic walls or mucus structures that basically held a burrow open in soft sediment. And a lot of them you can't really tell anything more than that, but that's probably what they are. They're just simple sinuous streaks going across the rock. Not all of them though. Some of them are worms. Some of them are algae. The majority though you just can't be sure of, and without decent evidence we didn't bother collecting them because they were everywhere in some intervals. Anything where we could be fairly certain what it was, though, of course, we collected. So in some cases, these were very clearly burrow linings, as in there's a different sediment in the centre. You can see that it is a flattened, but not completely flattened, ring of dark organic material surrounding a cylindrical tube. And in some cases, they were solid sheets, which you can't do a huge amount with, but that's what you'd expect. But in others, they got much more interesting. There are some that were made by sort of tangled strands, which actually look like little burrows themselves, but were limited to the burrow wall. So it appears that it's actually the texture of the sheet. Some of them have a consistent longitudinal pattern to them as well, which wouldn't really make so much sense if there were sort of micro burrows boring within the wall of the burrow. So we're pretty certain that these are actually the textures of the original burrow linings of whatever made these little burrows. And in some cases, there's also an infilling of tomaculum, little rounded pellets. Don't seem to have any photos of that, but I did a whole video on them from a different site in the built-in layer. And these, we think, were made by either priapulid worms or paleoscolecids, that sort of group of ecdysozoan worms, or possibly by annelids. Both of them can make little pellets and fill up burrows with them. So these lined burrows are not extremely soft tissue, but they are unusual. And when I say unusual, I mean you don't normally see them. So typically they are not preserved in mudstones of this age of the Welsh Basin or indeed anywhere else. So having lined burrows is a sign that you're getting something slightly unusual, even if you can't call it exceptional preservation. It's a start, though. It's interesting because they're not normally preservable. So many of the black streaks, though, were not burrow linings, we're pretty certain, because they showed other features that were much more unusual. Some of them we think were algae. Algae are a bit of a waste bucket in a lot of paleontology, in that if you find something which has got a bit of structure and looks like a scrap of seaweed, call it algae. But actually proving that it's algae is quite tricky. So we were quite limited in what we published, in which we said we were confident were algae. And we limited that to things that had features like a little stalk leading into a long sinuous frond, or thinning branches which are bifurcating into the sediment, but getting thinner at each stage, or a broad holdfast or float-like structure. And in one case, what we think was a fluting body, a slender thing coming off, then exploding into a bunch of little fibres. So all of those ones we're fairly confident are algae because it's very, very hard to squeeze them into anything else. And algae are quite interesting. It tells you that they came from somewhere where there was light. It was surface waters, relatively shallow. They might have been floating, of course. They might not have been on the seafloor. But there was some light somewhere, and they are, again, fairly soft. They're not the easiest things to preserve. So algae are a sign of some exceptional preservation. But some of the black streaks were indeed actually worms. So there were a few specimens, just a few, in 6 weeks of collecting, remember, of paleoscolecids. Partly preserved, incomplete ones, but with some really nice looking detail at the sclerotome. It's nice looking at first glance. Put them into an electron microscope and you find that all the fine detail is gone. You can see there's nodes on the plates. That's about it. No microplates, no platelets, no exquisite detail. So unfortunately, this is what you get when it's been effectively destroyed by metamorphism. So we've got paleoscolecids, but we can't do any taxonomy on them because there just isn't enough resolution there. You might be able to guess at a genus, but even that would be really pushing it, because with paleoscolecids you need fine detail. We also found some other ones, though, including a single specimen of a priapulid with scalids around the edge of the body and then a long, narrow proboscis coming out. And this one we're pretty confident on. It was only, I say, the one specimen, but there's enough detail in there that we were quite happy this was a priapulid. The reviewers were happy too. Then there were also random vermiform things, which that means worm-shaped, because we're not going any further than that. They may have been worms, they may not. There's one which seems to be a poorly preserved worm inside a burrow. It's very difficult to rule out some sort of weird concretionary effect, making an impression of a worm rather than a worm itself. You have to be very careful with that sort of stuff. So we didn't say a lot about that, but there were a few things at least that were definitely worms, which is nice, because the priapulid at least is soft body preservation. It's got a cuticle, but to preserve the proboscis as well is quite nice. You're getting some soft detail here. This is at least low-level Burgess-type preservation. The Shelly fossils are actually pretty standard for the early Ordovician and very similar to the Shinton shales that I mentioned as the lateral equivalent in Shropshire. We have a bit more than normal, though. So the brachiopods include multiple specimens with the pedicle preserved. This is a soft muscular stalk that they either burrow with or attach to a hard surface with. And those are unusual. You don't normally get the pedicles preserved except in proper lagostatin. We also had the gut preserved in a hyolith. This is a conical shell of slightly problematic affinities, but probably related to brachiopods and bryozoans and that sort of thing. And here we have a single phosphatized gut, which again is not unheard of. You do get this preserved in areas where there is some exceptional preservation. So it's nice. It's another component of the fauna. We got quite a lot of trilobites in the end, in total, but mostly just one or two species, and no soft tissues in any of them that we found. Quite a few articulated specimens, but they may have been either articulated molts or animals that died on the seafloor and decayed before they were buried. Of course, trilobites have a calcite skeleton, so although it's nice to get complete ones, it doesn't really count as exceptional. It certainly is not soft tissue. The same goes really for the echinoderms. So these are the relatives of starfish, sea urchins and so on, which have very, very delicate skeletons of calcite ossicles which collapse and disintegrate after the animal dies. And we actually have quite a high diversity of these, more than we put in the paper. And most of these are with a specialist who hopefully will be able to actually write them up at some point. But they are quite a nice selection of things like solutans, stylophodons, eocrinoids, glyptocystids. There's a range of them, and some disarticulated things that we'd also love to find a complete one of because they look like there's something interesting. But yeah, again, exceptional preservation to some extent in preserving complete echinoderms, but no soft tissue there. The echinoderms are actually a really popular group though, and not just with humans. It turns out that they were quite popular with some of the inhabitants of the Afon Gam Biota seafloor. So a few years ago, we described Echinocleptus, which was a worm of some sort, we presume annelid in fact, just based on similarity to modern things, which created a tube, an organic tube, very thin thing, but it stuck organic debris, skeletal debris, onto that tube. So bits of echinoderms. But it didn't stop there. Oh no. This one decided to stick complete living echinoderms onto its tube. Makes you wonder if they minded, but they probably didn't because they were just getting a boost up into the water column a bit. But we have, in some cases, complete little glyptocystids, little stalked echinoderms, which are embedded into these tubes. And we know it was done alive because some of them even have the brachioles preserved intact. So this thing, if it was already dead before it was stuck onto the tube, it would not have preserved the brachioles. They disintegrate within hours. So it's really quite amazing to have a worm wandering around on the seafloor, picking up any passing echinoderms and sticking them onto its tube. Presumably this was some sort of disguise type defensive mechanism that if you have little armed tentacly things attached to your tube, then it makes it less likely that they'll realise there's a nice tasty meal inside it. Anyway, that's quite a nice thing, and it turns out these agglutinated tubes, similar sorts of ones, although no others with the entire echinoderms, are actually quite common in the Early Ordovician. In China, in Morocco, there seems to be this little window in the Tremadocian to Florian where you end up with the same sort of pattern of worms for some reason started agglutinating particularly echinoderm debris onto their tubes, which is an interesting little anecdote. It doesn't seem to have happened much afterwards or before. It's just one little window when around the world it made sense ecologically. There was something else that made a robust tube as well, and this is a thing called oikobecilon, or something very close to it, which is a tube that is known from Silurian rocks. It's organic, it's strangely ridged, and it's got little projections on the side. It's quite a distinctive looking thing, and we have a few specimens of what appears to be oikobecilon. And yeah, it's peculiar. It's not been described from this age before. We weren't expecting to see it, and we don't know what made it. But one of the specimens seems to have a longitudinal tube going down the middle. And the preservation of that interior, although it's a little bit weathered, suggests that we might actually have the animal inside the tube, and that would be the gut going down the centre. It's either that, or possibly even this isn't a tube. It's some sort of really thickened outer cuticle around the worm itself. But we're not entirely sure what we're dealing with here, and hopefully one day a complete specimen will turn up showing the animal itself. But it's a nice little curiosity, that one. There are some other oddities I could mention as well. So we've got a circular, tetraradially symmetric, possibly, holdfast-like structure of unknown origin. It's thought, we've asked some specialists, that it is not a cnidarian because it seems to have a cuticle. It seems to have had a tough outer layer. And that's peculiar. I mean, it kind of vaguely looks like an Ediacaran frond holdfast in some ways. Not totally convinced of anything about this, but it's a strange thing. We've got a couple of specimens of holdfasty-like things. So there were other anomalies I could mention as well, things we just don't know quite what they are. But the main groups left to mention are the sponges and the non-trilobite arthropods. The comparison between them is interesting. So the sponges are extremely abundant in the Afon Gam Biota, abundant and diverse. Probably some 50-odd species there, although they're difficult to work with, which is one of the reasons I've not written them up entirely yet. The preservation is awkward. There's a lot of soft tissue, and there's not much skeleton. The spicules are often dissolved, crushed, difficult to make out, and it's the spicules you really need to do the taxonomy. So in this case, we've got too good preservation to be able to work with them. There's too much soft organic matter there, and the skeleton is badly degraded. But we can still say a reasonable amount. There's quite a number of things that look like Cambrian leftovers, things like coids and pyraniids, and hints of spongia, vallospongia. They're things which are known from the Cambrian. But then there are quite a large number of more complex-looking structures, which more closely resemble things like modern hexactinellids, but which are not diagnostic of any particular group of modern hexactinellids. So it looks like it's a whole swathe of things that are getting towards hexactinellids, crown group, but not there yet, probably. Or if they are, we can't really tell. It's a difficult set of fossils to work with, but they were abundant, they were diverse, and they were diversifying past what we see in the Cambrian deposits, which is interesting. That is a progression from the Cambrian Burgess Shale-type faunas. Then we come to the non-trilobite arthropods. In contrast, these are seriously rare. The only moderately common one is a bivalve carapace that was probably slightly mineralized based on the preservation, except that it looks like these might not be arthropods at all. We've since seen that there are rostroconch mollusks that apparently have a shell which is very similar down to this little notch in the corner there, a little groove. And this is awkward, because we also have seen some things described as bivalve arthropods, which actually have the trunk sticking out from Cambrian rocks, which also have a little groove at that corner. So is this arthropod? Is it rostroconch? Are some of the other ones assigned previously to some of these groups, one of the groups or the other, misassigned? We don't actually know what this is at the moment. It's going to have to take a little bit more work, and hopefully there'll be a definite answer from another deposit and we can work backwards from there. So that one, we're not sure. And we're left with other non-biomineralized arthropods, which are much, much harder to find. We hardly ever saw any of them. We got really excited. It was a good week if we found anything that looked like an arthropod. So the most complete one we have is what is believed to be a mollisoniid. It's not been described yet. There's some awkwardness in that the pygidium, which is normally quite diagnostic, would have to be prepared out, and it would have to be preparing through another bit of fossil, so it's slightly dubious. But it looks like it's a mollisoniid, which is a Cambrian group that is also known from the Fezouata Biota in Morocco, so it wouldn't be too big of a surprise. Next to it, though, is what Steve Pates recognised a few years later to be a radiodont appendage. Yes, these gigantic arthropods. This thing was 1.6 millimeters long, the appendage. And it seems to be one of the smallest radiodonts known, but it's still distinctive. It's a herdiid. The entire animal was probably about a centimetre or so, and we're not sure whether this was a juvenile or not, so we couldn't give it a name. But there were herdiids in the Fezouata. There were definitely herdiids in the Fezouata Biota in Morocco, but there were also herdiids in the Afon Gam Biota in North Wales, which is nice to see. They survived past the Cambrian in quite a few continents, probably. But certainly it wasn't just a polar refugium that we see in Morocco. Other arthropods are really extremely rare. We did have a trunk and a spined pygidium, but we lent it to an arthropod worker who will remain nameless, and he promptly lost it. So that one's never going to be seen again. There are bits and pieces too of other things, fragments or poorly preserved bits that we can't do much with. One or two might be a bit better, but also they are very hard to work with. Very hard to be certain what you're looking at, mainly because it's both poorly preserved and a single specimen. So with enough collecting, it would be possible to build up the diversity and describe some of the things that were there once you get 2 or 3 specimens. But it's not easy. And given how rare the arthropods are, having the mollisoniid and the radiodont appendage right next to each other is a bit of a novelty. You wouldn't expect that. 6 weeks of hammering thousands of blocks and you get 2 of them virtually in contact. However, we soon realised what was going on when we noticed they were actually both inside a burrow, along with bits of algal debris and so on. So probably something was using this burrow as a larder. And whether that was the original burrow maker, or whether it was the mollisoniid, which was dragging in bits of radiodont to chew on later, we don't know. But we do know that there's also another specimen of a burrow which has multiple of these tiny Shumadia trilobites inside it. And there it's a combination of molts and complete skeletons, so probably they were actually using that as a shelter and a place to molt safely. So we have this world in which there were quite a lot of lined burrows, agglutinated tubes, things which were structurally supported in the soft sea floor, and at least some animals were using those burrows as an extension of the sea floor. So it was an extra part of the environment, like sort of cave dwellers. And it's quite a nice little insight into how this ecosystem worked. There was more going on there than at first glance there might appear. So how do we go about summarising what we know about the Afon Gam Biota? Well, to start with, it's mediocre. It is a Burgess Shale-type biota in that it is the right sort of preservational style. We haven't studied the taphonomy yet in detail, but we think it's now sort of carbonaceous films plus the pyritization and maybe some other stuff going on as well with the metamorphic overprint. But it's basically within the Burgess Shale-type spectrum. And in the sense of the environment, it's also fitting perfectly within that sort of range. So it is a Burgess Shale-type biota. But it's not up there with the best of them because we don't have the softest creatures. We don't have much in the way of internal anatomy, just a very occasional gut in a hyolethe and that sort of thing. We don't have much fine detail of the external soft tissues. It's limited in a lot of ways. And therefore, we are certainly not seeing the full scope of this community. We're not seeing the full diversity that was there. It is a subset. Now, if you compare that with the Burgess Shale and Xinjiang biotas, for example, with 200 or 300 species or more, and you have all of the softest things you could possibly want being preserved, it's not at that level. If you include the 50-odd sponges, which of course you have to, then probably it's close to 100 species of exceptionally preserved or moderately well-preserved organisms. And that is definitely a tier below the best ones, maybe 2 tiers below. It's a sort of moderate to not thrillingly exciting Burgess Shale-type biota. However, it is better than quite a few other ones. So there are quite a few in the Cambrian that are really relatively poorly known, but have had quite a few papers studying them because it's part of our information set. And you don't ignore any exceptional preservation. It's just that some are better than others. And there are also some Ordovician ones, things like Tongao, Fengxiang, that also have much lower diversity than this and don't have the same range of soft tissue structures. So it's not bad. It's somewhere in the middle of the range of Burgess Shale-type preservation. The level of soft tissue preservation is actually broadly similar to what we see in the Fezouata Biota. It's a similar range where you don't get the truly soft-bodied animals preserved, at least hardly at all. The difference is that the Fezouata has been studied really intensively. It covers a huge area and they have far, far more material. And so it's probably much richer, but the level of preservation in terms of the details that are being preserved is not that dissimilar, which is interesting. Because that's something that we can then at least have some sort of comparison with. Now, it's important to note also that the exceptional preservation here occurs through quite a large thickness of rock across multiple sites over a kilometre or so, and we don't think that there is any major systematic bias against the things that it does preserve. So we don't think that there are just a few pockets where you get arthropods and most of the time they're not there, because of the distribution where we find them and because of the type of preservation, the style of preservation where we do see them. So we think that for the things that it is preserving, it's a reasonably representative assemblage that we're seeing. What does it tell us, though? Aside from interesting individual fossils, the main thing is the ecology. So in Cambrian faunas, arthropods tend to be the dominant group. And in terms of diversity and in terms of sheer abundance. And sponges are normally second, and then a range of other things depending on how good your preservation is. In the early Ordovician, it seems that in the Afon Gam Biota that has changed a bit, that we're seeing a higher proportion in abundance and diversity of sponges relative to arthropods. And we're also seeing diversification of other filter-feeding organisms. So we've got a lot of echinoderms, we've got a lot of brachiopods, and we're not seeing so much in the way of the predatory priapulids, just one specimen of those. So it looks like there's a shift towards suspension feeding, which is actually what you expect from the Great Ordovician biodiversification event, where it is predominantly associated with an increased abundance and diversification of suspension feeders. So this does look consistent with what we see later on in the Ordovician as a general pattern. We also have these peculiar extra things like the preponderance of tubes and lined burrows and things like that going. So there are unique little elements of this fauna that are different to what we see normally. There are some other bits and pieces, like bivalve arthropods seem to be diversifying as well, although we mostly just have a few fragments of those. So we can't say too much about them, but there are a reasonable diversity of bivalve carapaces, just not well preserved. So on its own, the Afon Gam Biota is limited in what it can tell us. It's really quite severely limited in some ways. It's not the best preserved and it's not the most abundant of Burgess Shale-type faunas, even in the Ordovician. But it's still significant because it gives us another data point, and we have few enough of them as it is. So the Fezouata is much, much better known and much more impressive based on what has been collected. But that is limited to the South Pole. And it's been uncertain whether this is representative of the rest of the world or is some sort of cold water refugium where things were clinging on there. And the Fezouata does show a combination of Cambrian-like elements of the fauna with much more derived Ordovician and more recent, more modern-looking organisms as well. So that's quite an interesting balance that we see in the Fezouata, which was why it became famous in the first place. And here we've got a much more Cambrian-like fauna, but with some elements diversifying. So we don't see many of the more derived, typically Ordovician groups there. And aglaspidid arthropods, for example, although those are known from the same formation at another site about 30 or 40 miles away. So aglaspidids did exist at this time in Avalonia as well, but they certainly weren't abundant in the Afon Gam Biota. So what this shows is that there are significant differences between what we see preserved in the Fezouata and the Afon Gam. Now, they were on different paleocontinents. One was polar, the other temperate, and they are somewhat different in age. The Fezouata is a little bit younger. Only a few million years, but then it ranges up another 5 or 6 or 7 million years beyond that as well. So it's significantly younger, in at least in the younger speds. But it does look as though the Afon Gam Biota was different. But we don't know how much of that is due to these differences in geography, in time, in paleoenvironment. We don't know whether one or the other is more representative of the rest of the world at the tropical or temperate latitudes, because we just don't have enough data points. We've got 2. That's not good enough. We now have the Castle Bank biota in the Middle Ordovician, but that's a very different time and a totally different community. Still, some elements are similar, like we're getting Cambrian holdovers still there and much more diversification in modern groups. So that's the overall pattern that we see in this early Ordovician phase. It is basically that the Cambrian Burgess Shale-type faunas did not just die out sometime in the late Cambrian. Most of them, or many elements of them, carried on and became incorporated into Ordovician communities. It seems to be different groups are being incorporated into different communities in different parts of the world. So maybe they're gradually declining, but then they get some holdovers in each place. And that seems to be the general pattern. There's a gradual replacement by the more modern groups that evolved during the Ordovician. And it had started even by the Tremadocian. So there you go. That is an introduction to the Afon Gam Biota and its ecological shift away from the Cambrian, while still remaining in large part a Cambrian community. And there may be biases. There are certainly unknowns. It's not one of the top tier of Burgess Shale-type biotas. But it just goes to show that you can get interesting information out of even the less promising types of deposits. And one day we're going to go back there and find some more, hopefully, and even write up some of the stuff that's sitting in our cellar in a big pile of boxes. Eventually. Once we finish the fieldwork. So the original paper for this, the one in 2015, is available open access. You can go and read it to your heart's content. Also, the one on the Herdiid is open access as well. So have a look at the description. You can go and look at those papers. And I'm hoping one day to have a whole series of videos about different Conservat Lagerstätten from this time period. It's gradually building up, but I'm mainly focusing on news stories so far, or ones that we've actually worked on. But there's lots more that we can cover and are looking forward to doing at some point. Right, I am going to go and not play tennis for a while, and hopefully we'll be back again in a few days or something like that with something different. And we are hoping to do this follow-up to the Dickinsonia at some point as well. So thank you for listening, and lovely to have you here, and farewell for now.